Okay, we're continuing inequalities, polynomial and rational inequalities, solving them, finding what x values make them true. We've so far done 2 examples. Here's the 3rd example. This is probably the most important one. This is our rational inequality. We've done a quadratic, we've done a polynomial, and actually a quadratic is a polynomial. So we've basically done 2 polynomial inequalities. This one is our rational inequality. I have chosen a quite difficult problem so that hopefully most of the problems you will encounter on the assignment are actually easier than this one. The hard part about this one is actually getting it in the right form. Since we have a 3 over here instead of a 0, that is the part that makes it difficult. If there's already a 0 there, it's really quite easy to do rational inequalities. So our first hardest part of this problem is getting a 0 on the right side. So that's going to take most of our effort here, subtracting the 3 from our rational problem on this side. Now we have to have a single fraction. So in order to turn this into a single fraction, we need a common denominator. Our common denominator is x plus 2. So we need to multiply the 3 over 1 by x plus 2 on the top and x plus 2 on the bottom. So we're basically multiplying by 1, which is not changing the value of the 3. Okay, next step is to go ahead and distribute the 3 and combine like terms. So we'll have 4x plus 5 minus 3x minus 6. That's a very key point right there that can cause lots of problems if you forget. Combining like terms, we get 4 minus 3 is just plain old x, and 5 minus 6 is a negative 1 over x plus 2. That is the problem we start with. So see, the main effort in this problem has been to get a problem that we can start with our fraction on the left and our 0 on the right. Okay, now we can find our critical values and solve. Critical values are actually quite easy to find. All you have to do is set your numerator equal to 0, because that will give you x-intercepts, and set your denominator equal to 0, because that will give you wholes and asymptotes. Okay, so x minus 1 equals 0. So x equals 1 is an x-intercept. Then we have the denominator. X plus 2 equals 0. So x equals negative 2 is an asymptote. Now here comes another tricky step. We have our critical values. The next step is to fill out our intervals, which we've done a couple times already, so it shouldn't be that hard. Let's start going. Negative infinity to negative 2. Stop. Look at our inequality sign. It's greater than or equal to. Shouldn't that mean that we can place a square bracket at the end of this problem? Well, typically that's what it means on polynomial functions, but on rational functions that is different. We have to stop and think. Is that critical value an x-intercept, or is that critical value an asymptote? Well, negative 2 is an asymptote. Therefore, the graph does not exist at negative 2. Even though this is greater than or equal to, the graph does not exist at negative 2 because that's an asymptote. So we do not put a square bracket, we put a parenthesis. And we always start where we left off. Now, when we get to our next critical value, 1, that is an x-intercept. Can the graph touch an x-intercept? Yes, by all means. That's what an x-intercept is where it touches. So since we are greater than or equal to, it can touch the x-intercept and be equal to that point. So this time we use a square bracket. And then of course we pick up where we left off until we get to infinity. So this one has a mixture of parentheses and brackets, and that is a very important part of the solution. Okay, now we can pick our test numbers, negative 3, 0, 2. We plug them into this answer here. Don't plug them into the original, because then it'll be greater than 3. plug them in here so that it's greater than 0. Okay, so we go negative 3 minus 1 over negative 3 plus 2. That gives us a negative 4 over negative 1, which is a positive 4. I care less about the fact that it's a positive 4 than I care about the fact that the answer is positive. That's the important part. So since this is positive and since our problem is greater than, that answer is true. Now we try our 0. 0 minus 1 is a negative 1. 0 plus 2 is a positive 2, so our answer is a negative 1/2. The important part is that it's negative, and a negative number is not greater than 0, and therefore that answer makes our inequality false. The next number is a positive 2, so we go 2 minus 1 is 1, and 2 plus 2 is 4. That gives us a positive 1/4. The main thing we care about is the fact that it's positive, and since positive is greater than 0, that makes our inequality true. So now we have this answer and this answer that make our inequality true. So our final solution is negative infinity to negative 2, square brackets, 1 to infinity.